The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. Well, we had an election since I saw you last. I hope you're happy about the results. I'm very happy, I guess. Except one thing. There was a senator who was in 18085, and he lost his seat. So we don't have a senator from 18085 anymore. It was Senator Sununu from New Hampshire, so he took 18085. Actually, it was a funny experience. Some years ago, I had to go to Washington to testify before the committee about increasing the funding for mathematics. So as I was nervous, of course, trying to remember what I'm going to say. More money is the main point, but you have to say it more delicately than that. And so I got in, and a lot of people are taking turns. You only get 5 minutes to do it. And so I went and sat down, waited for my turn. And here on the committee was my student, Senator Sununu. Well, at that time, I think Representative Sununu. So that was nice, somehow. He's a nice guy. Actually, the lobbyist who kind of guided me there, found the room for me and sort of told me what to do, said, "I hope you gave him an A." And the truth is, I didn't. So I guess you guys should all get A's just to be on the safe side. Or yeah, let me know if you're going to be in the Senate anyway. Or even. So there you go. Anyway, so he's all right. But he wasn't great in 18085. Okay, so you know what? This evening I just called the schedules office to confirm that it is tonight in 54-100. It's not a long, difficult exam, so see you at 7:30 or see you earlier at 4 o'clock for a review of everything that you want to ask about. So I won't try to do an exam review this morning. We've got lots to do, and we're into November already. So I want to finish the discussion of the fast Poisson solver, because it's just a neat idea, which is so simple. Anytime you have a nice square grid, I guess the message is anytime you have a nice square or rectangular grid, you should be thinking, use the fast Fourier transform somehow. And here it turns out that the eigenvectors are, for this problem, this K2D. So we're getting this matrix K2D, which is of size n squared by n squared, so a large matrix. But its eigenvectors will be, well, actually, they'll be sine functions for the K2D, the fixed, and they would be cosine functions for the B2D, free. And the point is, if the fast Fourier transform does all those fast. I mean, the fast Fourier transform is like set up for the complex exponentials, as we'll see in a couple of weeks. That's a key, that's the most important algorithm I could tell you about. Maybe after Gaussian elimination, I don't know. But my point here is that if you can do complex exponentials fast, you can do sines fast, you can do cosines fast, and that gives the result will be that instead of, I did an operation count when I did elimination in the order 1, 2, 3, 4, 5, 6, ordered by along each row. That gave us a matrix that I want to look at again, this K2D matrix. If I did elimination as it stands, I think the count was n to the fourth. I think the count was n. It was n size n squared. I had n squared columns to work on, and I think each column took n squared steps, so I was up to n to the fourth, and that's manageable. 2D problems, you really can use backslash. But for this particular problem, using the FFT way, it comes down to n squared log n. So that's way better, a big saving. In 1D, you don't see a saving, but in 2D, it's a big saving, and in 3D, an enormous saving. So a lot of people would like to try to use the FFT also when the region isn't a square. You can imagine all the thinking that goes into this. But we'll focus on the one where it's a square. Oh, one thing more to add. I spoke about reordering the unknowns. But you probably were wondering, okay, what's that about? Because I only just referred to it. Let me suggest an ordering, and you can tell me what the matrix K2D will look like in this ordering. I'll call it the red-black ordering. I guess with the election just behind us, I could call it the red-blue ordering. Okay, red-blue ordering. Okay, so the ordering, instead of ordering it by, let me draw this again. I'll put in a couple more. Make n equal 4 here, so I've got 16. N squared is now 16. So here's the idea. The red-blue ordering would is like a checkerboard. The checkerboard ordering you could think of. This will be 1, this will be 2, this will be 3, this will be 4, 5, 6, 7, 8. So I've numbered from 1 to 8, and now 9 to 16 will be the other guys. These will be 9, 10, 11, 12, 13, 14, 15, 16. So suppose I do that. What does K2D look like? Maybe you could, it's just like, it's a neat example. It gives us one more chance to look at this matrix. So K2D is always going to have 4s on the diagonal. So I have 16 4s. Whatever order I take, the equation at a typical point, like, say, this one, that's point number 1, 2, that's point number 3. At a point number 3, I have my 5-point molecule with a 4 in the middle, so there'll be a 4 on that position. And then I have the 4 guys around it, the -1s, and where will they appear in the matrix? With this ordering. So you get to see the point of an ordering. Yeah, so this was point 1, point 2, point 3. I'm focusing on point 3. It's got a 4 on the diagonal, and then it's got a -1, a -1, a -1, a -1. Where do they appear? Well, all those guys are what color? They're all colored blue, right? All the neighbors are colored blue. So I won't get to them until I've gone through the 8 reds, and then I come back to 9, whatever, 11, 12, 13. The point is they'll all be over here. So this is like, you see that the only nodes that are next to a red node are all blue, and the only nodes next to a blue node are all red. So this is sort of filled in a little bit. That's where I've sort of like 4 diagonals of -1s or something. But there you go. That gives you an idea of what a different ordering could be. And you see what will happen now with elimination. Elimination is completed already on this stuff. So with elimination, you want to push the non-zeros way to the end. That's sort of like the central idea is kind of a greedy approach, greedy algorithm. Use up zeros while the sun's shining, and then near the end, where the problem is elimination's reduced it to a much smaller problem, then you've got some work to do. So that's what would happen here. By the way, there's a movie on the 18086 page. I hope some of you guys will consider taking 18086. It's a smaller class. People do projects like creating this elimination movie. So that would be math.mit.edu/18, I think it's 086. And with the movie, has a movie of different orderings. To try to figure out what's the absolute best ordering with the absolute least fill-in is, you know, that's one of these NP hard combinatorial problems. But to get an ordering that's much better than by rows is not only doable but should be done. Yeah. Okay. So that's the ordering for elimination. This is for elimination. Okay. But that's a whole world of its own, ordering the thing for Gaussian elimination. My focus in this section 3.5, so this is section 3.5 of the book, and then this is section 3.6, which is our major one. That's our big deal. But my focus in 3.5 is first to try to see what the 2D matrix is. I mean, a big part of this course, I think, a big part of what I can do for you is to get comfortable with matrices. You know, sort of see, what do you look at when you see a matrix? What's its shape? What are its properties? And so this K2D is our first example of a 2D matrix, and it's highly structured. The point is, we'll have K2D matrices out of finite elements, but the finite elements might be, well, they could be those. This could be a finite element picture, and then the finite element matrix on such a regular mesh would be quite structured too. But if I cut them all up into triangles and I have a curved region and everything, an unstructured mesh, then I'll still have the good properties. This will still be symmetric, positive, definite, all the good stuff, but the FFT won't come in. Okay, so now I want to take a look again at this K2D matrix. Okay. So one way to describe the K2D matrix is the way I did last time, to kind of write down a typical row. Typical row in the middle has got a 4 on the diagonal and 4 minus 1s. And here we've reordered it so the 4 minus 1s came much later. But either way, that's what the matrix looks like. Let me go back to this ordering, and let's get 2D, a better, clearer look at K2D. I want to construct K2D from K, this is K1D. I don't use that name, but that's how here it is. Let me just show it to you. Okay, so let me take the matrix that does the second differences in the x direction. So this will be an n squared by n squared matrix, and it'll take second differences on every row. Let me just write in what it'll be. It'll be K, it'll be a block matrix, K, n blocks, each n by n. Do you see that will be the second difference matrix? That K takes the second differences along a row. This K will take the second x differences along the next row by row, simple. So this is the UXX part. Now what will the UYY, the second y derivative, that gives second differences up the columns, right? So what can I see what that matrix will look like, second differences up the columns? Well, I think it will look like this. It will have 2's on the diagonal, 2i, 2i, 2i. This is second differences, right, down to 2i. And next to it will be a minus the identity. Let me write it, and you see if you think it looks good. So minus the identity. It's like a K, a blown up K somehow, right? I have you see it's every row has got a 2 and 2 minus 1s. That's from the -1, the 2, and the -1 in the vertical second difference. But you see how the count, you see how the numbering changed it from here? Here the neighbors were right next to each other because we're ordering by rows. Here I have to wait a whole n to get the guy above. And I'm also n away from the guy below. So this is the 2 minus 1 minus 1 centered there above and below. Do you see that? If you think about it a little, that's not sort of difficult to see. And I guess the thing I want also to do is to tell you that there's a neat little MATLAB command, or a neat math idea really, and they just made a MATLAB command out of it, that produces this matrix and this one out of K. Can I tell you what this is? It's something you don't see in typical linear algebra courses. It's called, so I'm constructing K2D from K1D by what, this is called a Kronecker product. It's named after a guy, some dead German, or sometimes called tensor product. It's, the point is, this is always the simplest thing to do in 2 dimensions or 3 dimensions or so on, is like product of 1D things. Like copy the 1D idea both ways. That's all this thing is doing. Copying the one idea in the x direction and in the y direction. So the MATLAB command, I've got 2 pieces here. For this first piece, it's named after Kronecker, of, now let's see, I'm going to put in 2 n by n matrices, and Kronecker product is going to be a matrix, a giant matrix of size n squared, like these. Okay, so I want to write the right thing in there. I think the right thing is the identity and K. Okay, and so I have to explain what this tensor product, Kronecker product is. And this guy happens to be also a Kronecker product, but it's K and I. So I'm just like mentioning here that, because if you have 2D problems and 3D problems and they're on a nice square grid so you can like just take products of things, this is what you want to know about. Okay, so what is this Kronecker product? Kronecker product says, take the first matrix, I. It's n by n. Just n by n. That's the identity. Okay. And now, take this K and multiply every one of those numbers. These are all numbers. Let me put them in. Let me put more numbers in. So I've got 16 numbers. This is going to be like this is going to work for this mesh that has 4 guys in each direction and 4 directions, 4 levels. So it's I is 4 by 4 and K is 4 by 4. And now each number here gets multiplied by K. So because of all those zeros, I get just K, 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 which is exactly what I wanted. So that Kronecker product, just in one step, you've created an n squared by n squared matrix that you really would not want to type into, entry by entry. That would be a horrible idea. Okay, and if I follow the same principle here, I'll take the Kronecker product here, is I start with a matrix K. So I start with 2 minus 1 minus 1, 2 minus 1 minus 1, 2 minus 1 minus 1, 2, right? That's my K. And now what's the Kronecker idea? Each of those numbers gets multiplied by this matrix. So that 2 becomes 2I, minus 1 becomes minus I, minus 1 becomes minus I. You see it all clicks. And it's producing exactly the UYY part, the second part. So that's the good construction to tell you about. And the beauty is, I mean, this is just like cooked up, set up for separation of variables. If I want to know the eigenvalues and the eigenvectors of this thing, I start by knowing the eigenvalues and eigenvectors of K. Can you remind me what those are? Just like we should remember them. Anybody remember eigenvectors of K? Well, this is going back to section 1.5, way early in the semester, and I couldn't, there's a lot of writing involved, and I probably didn't do it all, but let me remind you the idea. We guessed those eigenvectors. And how did we guess them? We guessed them by comparing this difference equation to the differential equation. So and we're in 1D now. I'm just reminding you what we did a long time ago. Okay, so what did we do? I want to know the eigenvectors here of these guys. So I better know the eigenvectors of K, of the 1D one first. Okay, so what did we do in 1D? We found the eigenvectors of K by looking first at the differential equation minus u double prime equal lambda u with, and remember we're talking about the fixed here. And anybody remember the eigenvectors of this guy? Eigenfunctions, I guess I should say, for those. So sines and cosines look good here, right? Because you take their second derivative, it brings down a constant. And then do I want sines or cosines? Looking at the boundary conditions, that's going to tell me everything. I want sines. Cosines are wiped out by this first condition that u of 0 should be 0. And then the sine has to come back to 0 at 1. So the eigenfunctions were u equals the sine of something. I think, let's see, I want a multiple of pi, right? Pi kx. I think that would be right. Because at x equal 1, that's come back to 0. And the eigenvalue lambda, if I just plug that in, two derivatives bring down pi k twice, and with a minus, and that cancels that minus, so the eigenvalues were pi squared k squared, and that's the beautiful construction for differential equations. And these eigenfunctions are a complete set. It's all wonderful. So that's a model problem of what classical applied math does for Bessel's equation, Legendre's equation, a whole long list of things. Now, though all those equations that I just mentioned would have finite difference analogs, but to my knowledge, it's only this one, this simplest, best one of all. We could call it the Fourier equation if we needed a name for it. Yeah, I just thought of that. That sounds good to me. Fourier equation. Okay, so what's great about this one is that the eigenvectors in the matrix case are just found by sampling these functions. You're right on the dot if you just sample these functions. So for K, the eigenvectors, what do I call eigenvectors? Maybe y's. I think I sometimes call them y. So a typical eigenvector y would be a sign vector. I'm sampling it at, let's see, can I use h for this step size? So h is 1 over n plus 1 then, as we saw in the past. H is 1 over n plus 1. So I'm sampling, a typical eigenvector would sample this thing at h, 2h, sine of 2 pi kh, and so on, And that would be an eigenvector. That would be the eigenvector number k, actually. And do you see that that sort of eigenvector is like, it's well set up, it's gonna work because it ends, where does it end? Who's the last component of this eigenvector? It's sine n k pi k h. Sorry about all the symbols, but it's, you know, compared to most eigenvectors, this is like the greatest. Okay, now why do I like that? Because the pattern, what would be the next one if there was an n plus first? If there was an n plus first component, what would it be? What would be the sign of n plus 1 pi k h? That's the golden question. What would be, if I'm trying to say that these have a nice pattern because the guy that's the next person here would be sine of n plus 1 pi k h, which is what? So n plus 1 is in there, and h is in there. So what do I get from those guys? The n plus 1 h is just 1, right? N plus 1 h carries me all the way to the end. So that's a guy that's out. It's not in our matrix because that's a known one. That's a 0 in a fixed boundary condition. So like the next guy would be sine n plus 1 h. That's 1 sine pi k. And what is sine pi k? The sine of pi k is always 0. So we're getting it right. Like the guy that got knocked off following this pattern will be 0. And what about the guy that was knocked off of that end? That if this was sine 2 pi kh and sine pi kh, this would be sine 0 pi kh, which would be also 0, sine 0. So anyway, that you could check just by, it takes a little patience with trig identities. If I multiply k by that vector, the pattern keeps going, the 2 minus 1 minus 1. You know, at a typical point, I'm going to have 2 of these minus 1 of these minus 1 of these. And it'll look good. And when I get to the end, I'll have 2 minus 1 of these. The pattern will still hold because the minus 1 of these I can say is there, but it is a 0, so it's OK. And similarly here. Anyway, the pattern's good, and the eigenvalue is something. Okay, it has some formula. It's not going to be exactly this guy, right? Because we're taking differences of signs and not derivatives of signs. So it has some formula. Tell me what you know about lambda. I'm not going to ask you for the formula. I'm going to write it down. Tell me, before I write it down, or I'll write it down, and then you can tell me. I have 2 on the diagonal, so that's just going to give me a 2. And then the guy on the left and the guy on the right, 2 with minus 1s, I think gives 2. I think it turns out to be a cosine of k. A k has to be in there, a pi has to be in there, an h. I think that'll be it. I think that's the eigenvalue. That's the kth eigenvalue to go with this eigenvector. What do you notice about 2 minus 2 times the cosine of something? What is it, positive, negative, 0? What's up? 2 minus 2 times the cosine is always positive. What does that tell us about k that we already knew? It's positive definite, right? All the eigenvalues, here we actually know what they all are. They're all positive. I'm never going to get 0 here. These k pi h's are hitting points they're not hitting the ones where the cosine is 1. And of course, you can imagine. So I started this sentence and realized I should add another sentence. These are all positive. We expected that. We knew that k was a positive definite matrix. All its eigenvalues are positive, and now we actually know what they are. And if I had the matrix B instead for a free one, then this formula would change a little bit. And what would be different about B, the free matrix? Its eigenvectors would be, they're maybe at half angles or some darn thing happens. And so we get something slightly different here. Maybe h is 1 over n for that. I've forgotten. And what's the deal with the free case? One of the eigenvalues is 0, right? The free is the positive semi-definite example. Okay, that was like a quick review of stuff you remember we did earlier. And so I'm coming back to that early point in the book because of this great fact that I get that my eigenvectors are signs. So the point is, my eigenvectors being signs, that just lights up a light saying, use the fast Fourier transform. You got a matrix full of sign vectors. Your eigenvector matrix is a sign transform. It's golden, so use it. So I'll just remember then how, recall that. So what are the eigenvectors in 2D? Yeah, first of all, so let's go to 2D. Let me do the continuous one first. Yeah, minus uxx minus uyy equal lambda u. The eigenvalue problem for Laplace's equation now in 2D. And again, I'm going to make it on the square, this unit square, and I'm going to have 0 boundary conditions, fixed. Anybody want to propose an eigenfunction for the 2D problem? So the 2D one, the whole idea is, hey, this square is like a product of intervals somehow. We know the answer in each direction. What do you figure? What would be a good eigenfunction u of x and y, or the eigenfunction, yeah, u of x and y, for this problem? What do you think? This is like the older courses on applied math did this, until you were blue in the face, because there wasn't finite elements and good stuff at that time. It was exact formulas. You wondered about exact eigenfunctions, and for this problem, variables separate, and you get u of x is the product of sine of this guy, sine pi kx, times a sine of pi ly. Well, once you have the idea that it might look like that, you just plug it in to see, does it really work, and what's the eigenvalue? So I claim that that's a good eigenfunction, and it's got 2 indices, k and l, 2 frequencies. It's got an x frequency and a y frequency. So I need double index. K and L will go, all the way out to infinity in the continuous problem. And what's the eigenvector? Can you plug this guy in? What happens when you plug that in? Take the second x derivative. What happens? A constant comes out, and what's the constant? Pi squared k squared. Then plug it into that term. A constant comes out again. What's that constant? Pi squared L squared. They come out with a minus, and then you already built in the minus so that made it a plus. So the lambda KL is just pi squared k squared plus pi squared L squared. You see how it's going if we knew it in 1D, now we get it in 2D, practically for free. Just the idea of doing this. Okay, and now I'm going to do it for finite differences. So now I have K2D. And I want to ask you about its eigenvectors, and what do you think they are? Well, of course, they're just like those. They're just the eigenvectors, shall I call them ZKL. So these will be the eigenvectors. The eigenvectors ZKL will be their components. I don't even know the best way to write them. The trouble is, this matrix is of size n squared. Its eigenvectors have got n squared components. And what are they? Just, you could tell me in words. What do you figure are going to be the components of the eigenvectors in K2D when you know them in K, you know them in 1D? Products, of course. this construction, however I write it, is just like this. ZKL, typical components, so that components of the eigenvectors are products of whatever of these guys, like sine, k, pi, h, something like that. I've got indices that I don't want to get into. Just, damn it, I'll just put that, right? Sine here or something, right? We could try to sort out the indices. The truth is, the cron operation does it for us. Yeah, so all I'm saying is we've got an eigenvector with n components in the x direction. We've got another one with index L, n components in the y direction. Multiply these n guys by these n guys, you get n squared guys, whatever order you write them in, and that's the eigenvector. And then the eigenvalue is, so the eigenvalue will be, well, what do we got? We have a second x difference, so will be a 2 minus 2 cosine k pi h from the xx term, and it'll plus the other term will be a 2 minus 2 cosine L pi h. That's cool. Yeah, I didn't get into writing the details of the eigenvector. That's a mess. This is not a mess. This is nice. What do I see again? I see 4 coming from the diagonal. I see 2 minus 1s coming from left and right. I see 2 minus 1s coming from up and below. And do I see a positive number? You bet, right? This is positive. This is positive. Sum is positive. The sum of 2 positive definite matrices is positive definite. I know everything about K. And the fast Fourier transform makes all those calculations possible. So maybe just to conclude this subject would be to remind you, how do you use the eigenvalues and eigenvectors in solving an equation? I guess I better put that on a board, but this is what we did last time. So the final step would be, how do I solve K2D U equals F? You remember what were the 3 steps? I do really want you to learn those 3 steps. It's the way eigenvectors and eigenvalues are used. It's the whole point of finding them. The whole point of finding them is to split this problem into n squared little 1D problems where each eigenvector is just doing its own thing. So what do? You write F as a combination with some coefficients CKL of the eigenvectors YKL. So these are vectors. I'll put an arrow over them just to emphasize. Those are vectors. Then what's the answer? Let's do it. Let's skip the middle step, which was so easy. Tell me the answer. Suppose the right-hand side is a combination of eigenvectors. Then the left-hand side, the answer, is also a combination of eigenvectors. And just tell me what are the coefficients in that combination. This is like the whole idea is on 2 simple lines here. The coefficient there is what do I have? CKL, does it come in? Yes, because CKL tells me how much of this eigenvector is here. But now what else comes in? Lambda KL, and what do I do with that? Divide by it, because when I multiply, that'll multiply by it and bring back F. So there you go. This U is a vector, of course. These are all vectors. 2D, we'll give them an arrow to as a reminder that these are vectors with n squared components. They're giant vectors. But the point is this YKL, its n squared components are just products, as we saw here, of the 1D problem. So the fast Fourier transform, the 2D fast Fourier transform just takes off. Takes off and gives you this fantastic speed. Yeah, so that's absolutely the right way to solve the problem. And everybody sees that picture? Don't forget that picture. That's like a nice part of this subject, is to get it's formulas and not code, but it's easily turned into code because the FFT and the sign transform are all coded. Actually, Professor Johnson in the math department, he created that's the best FFT code there is. Do you know that? I'll just mention. So his code is called FFTW, the fastest Fourier transform in the West. And the point is, it's set up to be fast on whatever computer, whatever architecture you're using. It figures out what that is, optimizes the code for that, and gives you the answer. Okay, that's part 2 complete of section 3.5. I guess I'm hoping after we get through the quiz, the next step, natural step, would be some MATLAB, right? We really should have some MATLAB case of doing this. I haven't thought of it, but I'll try. And some MATLAB for finite elements. And there's a lot of finite element code on the course page, so for you ready to download. But now we have to understand it. Are you ready to tackle? So in 10 minutes, we can get the central idea of finite elements in 2D. And then after the quiz, when our minds are clear again, we'll do it properly Friday. Can I, this is asking you a lot, but can I do it? Can I go to finite elements in 2D? Okay. Well, I have a choice, big choice. I could use triangles or quads. That picture, this picture, would naturally set up for quads. Let me start with triangles. So I have some region with lots of triangles here. Got to have some interior points or I'm not going to have any unknowns. Gosh, that's a big mesh with very little unknown. Let me put in another view here. Have I got enough? Oops, that's not a triangle. How's that? Is that now a triangulation? So that's an unstructured triangular mesh. Its quality is not too bad. The angles, some angles are small, but not very small. And nor are they, and I guess all the, yeah, and they're not near, that angle's getting a little big too, it's getting toward 180 degrees, which you have to stay away from. You know, if it was 180, the triangle would compress would squash in. So it's a bit squashed, that one. This one's a little long and narrow, but not bad. And you need a mesh generator to generate a mesh like this. And I had a thesis student just a few years ago who wrote a nice mesh generator in MATLAB. So we get a mesh. Okay. Now, do you remember the finite element idea? Well, first you have to use the weak form. Let's save the weak form for first thing Friday. The weak form of Laplace. I need the weak form of Laplace's equation. I'll just tell you what it is. We'll have double integrals. Or Poisson. I'm making it Poisson. I want a right-hand side. Okay. Double integral. This will be d. This will be du dx, the test function dx, And now what's changed in 2D, I'll also have a du dy, dv dy, dx dy. That's what I'll get. And on the right-hand side, I'll just have f, the load, times the test, dx dy. Yeah, I guess I have to write that down because that's our starting point. Do you remember the situation? And of course, that's on the exam this evening, is remembering about the weak form in 1D. So in 2D, I expect to see x's and y's. My functions are functions of x and y. I have this is my solution. The v's are all possible test functions. And this holds for this is like the virtual work. This is you could call it the equation of virtual work if you were a little old-fashioned. Those v's are virtual displacements. They're test functions. That's what it looks like. I'll come back to that at the start of Friday. What's the finite element idea? Just as in 1D, the finite element idea is choose some trial functions, right? Choose some trial functions. And our approximate guy is going to be some combination of these trial functions. Some coefficient u1 times the first trial function, plus so on, plus u sub n times the nth trial function. So this will be and these will also be our test functions again. These will also be, the phis are also the v's. I'll get n equations by using n tests, by using the weak form n times for these n functions, and so each equation comes, v is one of the phis, u is this combination of phis, plug it in, you get an equation. What am I going to do in 3 minutes is speak about the most important point, the phis. Choosing the phis is what mattered. That's what made finite elements win. The fact that I could choose nice, simple functions which are polynomials, little easy polynomials on each element, on each triangle. And the ones I'm going to speak about today are the linear ones. They're like hat functions, right? But now we're in 2D. They're going to be pyramids. So if I take, this is unknown number 1. Unknown number 1, it's got its hat function, pyramid function, sorry, it's pyramid function. So its pyramid function is a 1 there, right? The pyramid, the top of the pyramid is over that point, and it goes down to 0, so it's 0 at all these points, at all the other points. That's the one beauty of finite elements, is that then this coefficient u1 that we compute will actually be our approximation at this point, because all the others are 0 at that point. So can you just, this is all you have to do in the last 60 seconds, is visualize this function. Do you see it? Maybe tent would be better than pyramid, either one. What's the base of the pyramid? The base of the pyramid I'm thinking of this surface as a way to visualize this function. It's a function that's 1 here. It goes down to 0 linearly. So these are linear triangular elements. What's the base of the pyramid? Just this, right? That's the base. Because over in these other triangles, nothing ever got off 0. Nothing got off the ground. It's 0, 0, 0 at all 3. If I know it at all 3 corners, I know it everywhere. For a linear function, it's just a piece of flat roof. Piece of flat roof. So I have, how many pieces have I got around this point? Ooh, where's the point? I guess I've got 1, 2, 3, 4, 5, 6, is it? It's a 6. It's a pyramid with 6 sloping faces, sloping down to 0 along the sides. Right, so it's like a 6-sided TP, 6-sided tent, and here are the rods that hold the tent up would be these 6 things, and then the 6 sides would be 6 flat pieces. If you see what I've tried to draw there, that's phi1, and you can imagine that when I've got that, I can take the x derivative and the y derivative. What will I know about the x derivative and the y derivative in a typical triangle? If my function is in a typical triangle, say in this triangle, my function looks like a plus bx plus cy. A plus bx, it's flat. It's linear. And these 3 numbers a and b are decided by the fact that the function should be 1 there, 0 there, and 0 there. 3 facts about the function, 3 coefficients to match those facts. And what's the deal on the x derivative? It's just b. It's a constant. The y derivative is just c, a constant. So the integrals are easy, and the whole finite element system just goes smoothly. So what the finite element system has to do, and we'll talk about it Friday, is got to keep track of which triangles go to which nodes, how do you assemble them, where do these pieces go in. But every element matrix is going to be simple. Okay.